Let's start with carboxylic acid chapter today. See what we can do. Sorry, check. When it comes to carboxylic acid, first thing we need to know is all the important common names. Right? Starting with first one, formic acid, acetic acid. This is 4 carbons, so this is butyric acid. This is valeric acid, oxalic acid, and see for dioic acids, as you start increasing one carbon, each carbon has, each molecule has a different name. This is malonic acid, succinic acid, glutaric acid, adipic acid, and this is pimelic acid. These are all the acids. Next, in case if you have a succinic acid with a double bond here, the cis form of it is called as malic acid. Trans form is called as fumaric acid. This one is benzoic acid. If you have two COH, it is called phthalic acid. If it is at meta position, it is isophthalic acid. If it is at para position, it is terphthalic acid. And if you have a cyclic amide group like this, these hydrogens are also sufficiently acidic. This is not a carboxylic acid. It is called barbutyric acid. Barbutyric acid. This is the first list of acids we should know. Next, if you have COOH and one NH2 at the ortho position, this is anthracnalic acid. If we have a chiral molecule with CH3H and OH with COOH, this is called lactic acid. And if you have OH and OH on with dioic acid here, this is tartaric acid. Tartaric acid. And in case if you have, sorry, here it should have been COOH. So in case if you have 3 COOH groups and one OH group here, this is called citric acid. This is citric acid. Got it? Done. These are the common acids that we must know. Next, preparation wise, these are all repeat reactions now. Check out. If you want to prepare acids from alkanes, there is hardly much reactions. Manganic acetate on heating with oxygen, alkanes can get oxidized to acids. This reaction is given in alkanes topic also in NCERT as a reactions of alkanes. Next, from alkenes. If I take hot concentrated KMNO4 or K2Cr2O7 and H+, they would help in breaking the bond, convert them into acids. If it was a single carbon, it cannot stop at acid, it will eventually convert to carbon dioxide. So you can see if you break here, you'll get two types of acids here. If we are performing oxidative ozonolysis, and oxidative ozonolysis include either we have only water or peroxide, In that case, after breaking, both will convert into acids. Next one is Koch reaction. Koch reaction is when you have an alkene react with CO and HCl in the presence of AlCl3, followed by hydrolysis. We will get this as acid. Let me show the mechanism, how it works. R RCH double bond CH2 and alkene. If you see HCl with AlCl3, lone pair of oxygen, lone pair of chlorine can connect here. That will break this bond, and that's when the pi bond can connect from the other end. This will create a carbocation, RCH plus and CH3, following Markovnikov's addition. And the carbon monoxide which is present here, C triple bond O minus and plus, this can be used as a nucleophile to attack on this position. You will get this as RCH CH3 with C triple bond O plus. It is highly unstable form, so H2O will attack on this position of carbon to pull away the low pi bond towards oxygen. So we'll get CH, CH3 and COOH. That's how we can get acids. This is called Koch reaction. I hope everybody understood that. The next reaction is from alkynes. Alkynes can also be oxidized using O3 or KMnO4. KMnO4 can be either in acidic medium or a basic medium. Both will be able to break the bonds and convert into acids. Alkyl halides first need to be converted into Grignard's reagent using magnesium and ether. And then when you react with carbon dioxide, they will convert into a carboxylate salts, and which on hydrolysis will give you acids. So simple reaction. Another way is first making alkyl halides to undergo a nucleophilic substitution like this with cyanides. And cyanides are specifically used as they undergo hydrolysis in acidic medium or a basic medium. First thing they will form is amides, and amides on further hydrolysis will eventually convert into acids. Only one thing you need to take care is that in a basic medium, the reaction will be slower, so we require heat to convert them into acid form. If concentrated H2SO4 is given, it can directly give you acids. There is not much stoppage at amides. In case if at all we are using this instead of water, if at all I use ethanol, we will be ending up getting esters. Okay. This part of the mechanism is there for your syllabus, there in your syllabus. So let's see how the cyanide gets hydrolyzed. First, in acidic medium, RC triple bond N, lone pair will take H plus in acidic medium. And as it takes H plus, it will become RC triple bond NH plus. That allows water to attack as a nucleophile on carbon, push these electrons towards nitrogen, makes this RCOH double bond NH. Basically here proton transfer is happening, OH2 plus, and this is the way it is. And that proton transfer will happen towards nitrogen, making it into NH2 plus. As it becomes NH2 plus, the lone pair will again push and electrons will migrate towards nitrogen, converting that into C double bond O plus and NH2. This will undergo further IMPT making that into Rc double bond O NH3 plus. Or before making an IMPT, what I would suggest, if the amount of acid is limited, you can easily isolate it, keep it in aqua solution with a very limited amount of acid. You can isolate this into amides. So amide is an intermediate here. But in case if you keep sufficient amount of acids, it will continue to go through intra IMPT, and NH3 plus is a good leaving group now. So water can attack on the carbon here, and that helps in removing NH3. And thus we will get it as Rc double bond O OH2 plus and ammonia. Now you can see this is more like an acid base reaction again, giving you Rc double bond O OH plus NH4 plus. So in the product, we would always report these two. So on acidic hydrolysis, we'll report acid and ammonium ion or ammonium salt. Clear? This is how the mechanism works in acidic medium. Have a quick look. Okay, let's now look into basic medium. In case if you are conducting hydrolysis in basic medium, how does that take place? Rc triple bond N with OH minus. As a nucleophile, it will attack here. Pi bond will shift, and this will give you RCOH double bond N minus. This N minus can fetch H plus from water, and that will convert it. Sorry, can fetch H plus from water, and that will convert into RCOH double bond NH. And this can be further tautomerized. So due to tautomerization, we will get this as C double bond O and NH2. So you can see here, amide is also an intermediate which is easily removed out. But if you have sufficient concentration of OH minus and you are providing heat to it, and if you are providing heat to it, then chances are first you will get an addition reaction here like this OH and NH2, and thereafter on heating this NH2 would come out. Okay, this is where exactly the heat is essential. That will make it Rc double bond O OH plus NH2 minus. NH2 minus is a very strong base. It can take H plus, convert the product into RCOO minus and NH3. This is the final product. Please check. As a final products, we will be reporting these two. Right. See the next one. If I want to get carboxylic acid on benzene, we have to go through side chain oxidation. We can use KMnO4 K2Cr2O7 either in acidic medium or a basic medium. I mean, not K2Cr2O7. We can use KMnO4 in basic medium also. The requirement is we must have at least one alpha hydrogen for sp3 carbons. So let's put this as a note. Okay. At least one alpha hydrogen must be present on uh, sp3 carbon sp3 carbon to initiate the oxidation. So you can clearly notice that this carbon has 3, this has 2, this has 1. And the oxidation would happen such a way even carbon-carbon bond will break here. It can break here, here, and they all will convert into COH. After breaking, if you have a single carbon, that will convert into carbon dioxide. Here also after breaking, if you have a single carbon, that will convert into carbon dioxide. Break here, single carbon converts into carbon dioxide. Now notice there is no hydrogen here. That's why there is no reaction. Now it does not matter whether there is any other functional group on it. It will still break. So OH will be there. It will still break. OCH3 is there. Still break. Aldehyde is there. Ketone is there. They all will break and convert into acids. If you have two methyl groups, you will get phthalic acid. If you have a ring form here, even then the bond breaking will happen here. So first you will get phthalic acid and you will get actually an oxalic acid. But oxalic acid, if you keep it while for MnO4 minus, it will convert into carbon dioxide. So these two carbons you will report as carbon dioxide. So let me mark them. This carbon, and this carbon. Those two will convert into carbon dioxide. Same way here, in the next case, we can have this carbon, as well as this carbon. All these three will convert into carbon dioxide. In case if you have two fused rings, the ring which is more activated, in this case, in alpha naphthol, this ring is more activated. That ring will get oxidized. So bond will break here, and you'll get phthalic acid, carbon dioxide. If you have nitro, then this ring is more activated. The ring which is more activated will break, and that will convert into acids. So you'll get this nitrophthalic acid. If you have cyclic ketones will also break very easily, and they will break it into formation of this acid. It's a 6-carbon acid, so which is called as adipic acid. Okay, all these are side chain oxidations. If you may recall, we have done this same thing in benzene already. Next, how do we get acids from alcohols? If you have 1 degree, simple oxidation will lead to acids. All these are oxidizing agents. KMnO4, K2Cr2O7, CrO3 in acidic medium with acetone, which we call it as Jones reagent. We can use concentrated HNO3 also. In fact, if you simply given CrO3 plus H plus, okay, or H2CrO4, both these forms are always taken for complete oxidation. So that will convert into carboxylic acid. In case of secondary alcohol here, and we treat with I2NaOH, it will go through iodoform reaction. So this carbon will convert into iodoform. Rest of the part will convert into acids. Same thing here also. This carbon will convert into iodoform. The rest of the part is converting into acids. If you have alcohol, in the case of calcium hydroxide, again this form will convert into iodoform. The rest of the part will convert into calcium uh, salt. If you may remember, in aldehydes and ketones, we learned the preparation of ketones from dry distillation. So in case if the reaction is continued and heat is given to do dry distillation, instead of acid salt, calcium salt, we will report that as ketone. Okay. This is the mechanism. If you may remember, calcium oxide will go away, carbon dioxide will go away, this minus will attack here. That's how we can get ketone. If you have this alcohol, again I'll get this CO minus. One important thing to note is that it does not disturb the double bond. So double bond will be intact and CO minus is formed. So especially when you do not want the double bond to get disturbed, then this is a better way to get the acids from alcohols. Okay. These are all the reactions of alcohols converting into an acid. Next, let's see how aldehydes and ketones will convert into acids. We already learned this in the last topic that either use KMnO4, K2Cr2O7, Tollens reagent, Fehling's reagent, or Benedict reagent. They all will undergo oxidation to make aldehydes to carboxylic acids. And even if you have a simple aldehyde here, without disturbing double bond, if you want to make, then it is Tollens, Fehling's, and Benedict. This is a new reaction, that is Ernst-Eisterd reaction. We use acid chlorides to convert into an acid with an increased carbon chain. Okay. So I want one extra carbon to be made. In that case, the product what you will get in this reaction, the product what you will get here is RC double bond O. Okay. Sorry, RCH2, RCH2, C double bond O, and OH. Okay. Depending upon whether you are doing hydrolysis or not. Got it? Let me show you the mechanism, how it works. So first we have R C double bond OCl treated with diazomethane. Diazomethane will have a structure like this, CH2 minus and N2 plus. And diazomethane is a good nucleophile. It can attack here, remove chloride from here. And that will make the reaction to convert into R C double bond O CH2 N2 plus N2 plus. Okay. Now you can see this is a highly activated methylene position. Okay. That's the reason why Ag2O moist is used. So Ag2O moist is another way of representing that there is OH minus. That OH minus will attack here. And why only Ag2O is that the chloride which has removed can be easily precipitated by silver. And on doing that, we will get this as R C double bond O CH minus and N2 plus. Now here is an interesting fact. Once you get this kind of a situation where you have a C double bond O, adjacent carbon has negative charge, and then we have a good leaving group. In that case, a rearrangement will take place from here. This R minus will attack here. This lone pair will make into a double bond, while this N2 will go away. Okay. This is called Wolff rearrangement. Wolff rearrangement. So due to this Wolff rearrangement, what do we get here? So we will get this as RCH double bond C double bond O plus N2. Correct? This is like a ketone with a double bond. Ketone with a double bond is called as ketene. This is the intermediate form. Okay. Now, ketene, making a ketene gives us a leverage of getting a lot of products. For example, check here. If I take this ketene here and make a reaction with H2O, so how does it proceed? C double bond O, and if you have water, H2O will attack here, minus charge will go here, and you'll get CH minus COH2 and double bond O, and that minus will take H plus, convert into RCH2, double bond O and OH. So I think you got an idea that this nucleophile will go attack on the carbon. And see, if water attacks, you'll get acid. If ammonia attacks, you'll get amides and so on. So let me directly write the product now. So for these ketenes, if I want to get any product here, so first will be RCH2COOH. This will be RCH2CONH2. Here it will be RCH2COOR dash. It will be RCH2COCl. Here this will be RCH2COOR dash. Okay, sorry, RCH2O, RCH2CO, C double bond O R dash, like this. That is an anhydride form. So you'll get this as an anhydride form. Correct. So especially if you want to increase a carbon length, along with that you want to get any carboxylic derivative, this is the best reaction. Clear, everybody? Done. Next, notice. In case if you have any acid derivatives and you perform hydrolysis, the reason why we call this as acid derivatives is that they should give acid on hydrolysis. And which is what it does. Acid chloride, amides, esters, cyanides, and anhydrides. All of them on hydrolysis are giving carboxylic acids. And if you have an acid chloride on hydrolysis, you'll get acid and HCl. And if you have it in basic medium, you will get this as acid salts and chloride salts, which again on hydrolysis will give you acids. Got it? So please go through these two reactions quickly. Now see, the way we have done it for hydroxy groups is the same way we'll do it for amino acids also, alpha amino acids and so on. Starting with first alpha amino acids. Okay. What do we get? I told you whenever it is alpha, you'll go for more cyclic formation. Okay. So again, same thing here. We can make this as double bond O and OH, and other end I can write it as NH and H. Here also I can write NH and like this with double bond O and OH. So you can see this gets dehydrated. This part will get dehydrated. Combining both of them, we will get a double bond O with NH. Here it is NH, double bond O, like this. This is the product which you will get. Again, just like earlier case when you have hydroxy, here also we can have three products. Here two methyl groups coming out of the plane, or I can have two methyl groups going inside the plane. or one inside and one outside, which is a mesoform. This one, this is meso. It is meso because of center of symmetry. And these two would be optically active. These two will be optically active. Okay. So these are cyclic amides, cyclic in fact diamides. So these are called dilactams. Dilactam. Lactam is a term that is used for cyclic amides. Just like how it operates for hydroxy acids. Now, if you have amino acids at beta position, we will make an alkene here. Make this as COOH plus NH3. Okay, COOH and NH3. In case if you have, at gamma position, so we will have it like this: NH connected to C double bond O, and then I'll make a 5-membered ring like this. So this is a uh, gamma lactam. This is gamma lactam. And in this case, we can have double bond O this way, and this will become delta lactam. This is derived from delta, so delta lactam. These are all amides only. Similarly, if it goes 5 and above, it will get polymerized. So you'll get CH2 X times C double bond O here, and it extends N times here, N moles of it. So this is called as polyamides. The esters are the polymers are called as polyamides, right? So all these are very similar result what we got it earlier. So starting with alpha amino acids, beta amino acids, gamma, delta, epsilon. Next, what happens if you take the action of heat on dicarboxylic acids? Starting with beta dicarboxylic acid. That is, if you have COOH and COOH. So with respect to one COOH, the next carbon is alpha, the other carbon is beta. This on heating, what would happen? So you can notice that we have O, which has lone pairs on it, and then we have OH, and here we have O and H with a double bond O. Now you can see this lone pair will take H plus, this will convert into double bond, this will push here, the pi bond will push onto oxygen. So this rearrangement will lead to the formation of OH here, OH here, double bond here, plus CO2. This is an enol form. Enol is unstable, so it will convert into a keto form, which is C double bond O CH3, and other side we have OH anyway. So what do we get? An acid. So diacid will convert into monoacid with carbon dioxide. So this is also a decarboxylation reaction. It will undergo decarboxylation here. Correct. Next, let us see about gamma dicarboxylic acids. Okay, that is, if you have OH and two other carbons here with double bond OH here and double bond O. Now, this is nothing but succinic acid, right? We remember the name succinic acid. Succinic acid on heating will convert into, you know, N here, sorry, O here, double bond O and double bond O this way. What is this one? This is called succinic anhydride. Succinic anhydride. Succinic anhydride. Similarly, if you have delta dicarboxylic acids, so we will have this as CH2 three times and that is connected to COOH and COOH. What did we call this? We call it as glutaric acid. And glutaric acid on heating, okay, if you see glutaric acid on heating, what do we get? See, glutaric acid on heating will give us an anhydride, same type of anhydride here. So that will be 6-membered ring now. Double bond O like this way, a 6-membered ring. So this is glutaric anhydride, glutaric anhydride. So, sorry, check. So this is glutaric anhydride is what we will get. Next, if we have epsilon dicarboxylic acids, so that is if you have CH2 4 times, and then we have COOH and COOH. We call this as adipic acid. If you heat adipic acid, now 6-membered is already done. So this is very interesting to see that now what happens is, because it cannot undergo an anhydride form, it would actually get decarboxylated. So if it get decarboxylated, the product that you will observe is a ketone, 5-membered ring ketone and CO2. Okay, this is what you will get. And the same way, after epsilon, correct? The next molecule which you will have is CH2 5 times, and then we'll have COOH and COH, which we call it as pimelic acid. So if you are heating pimelic acid, then the same logic would be applied. This time you'll get 6-membered ring and carbon dioxide. So this is one very important thing to notice. If you want to get an I mean decarboxylation done from dioic acids, okay, then which are all the cases you can do? Case one, which is beta dicarboxylic acid. Then we have fourth case, and then we have fifth case. In these three cases, we will notice decarboxylation is done. Okay. These are all, by the way, whatever we are doing is all heating effects. Okay. Now, so next one we will see is further heating, but this time focus is only on decarboxylation reactions. So you can see first soda lime decarboxylation. By the way, everything is repeat reactions. That's why I'm going fast. So all these we have learned in alkanes or alkenes. Here, decarboxylation is when you take an acid, react with NaOH, it will convert into an carboxylate. And this, when you heat further with NaOH and CaO at the ratio of 3 is to 1, that will convert into an alkane and Na2CO3. Okay, this is a product formation. If you recall the mechanism, the first step the first step is about RC double bond O minus, which on strong heating will give you an carbanion. So strong heating will give you minus and CO2. So you get this as R minus and CO2. So formation of this itself is a challenging part. So therefore, this is the rate determining step. Okay. So R minus what you get here will be hydrolyzed and converted into RH plus OH minus. Okay. And in fact, the carbon dioxide and OH minus in the solution is what converts into CO3 2 minus. So these are the reaction steps that will take place. So I can say that rate of SLDC, rate of soda lime decarboxylation, is directly proportional to stability of anion. Stability of anion. Okay. On that note, just let me recall this example once. If you have COO minus Na plus salt with some group G, as long as this group is withdrawing, it will stabilize the carbanion. So G, in case if you have NO2, it will be strongly withdrawing, then cyanide, then chlorides, then hydrogen. And from CH3 onwards, it is donating OCH3, OH, and NH2. So this is the order in which soda lime decarboxylation is being done. Critical charge. Second. Finished? Everybody check soda lime decarboxylation. Just a second. Sorry. Check. Next. Next, decarboxylation is done by beta keto acids. That is, if you have double bond O, double bond O, and OH here. So this is beta keto acid. Beta keto acid on heating, it will get easily decarboxylated and convert into CO2. The mechanism based is the same as we learned earlier. O and H here, double bond O. So on strong heating, this oxygen will take H plus. Here you will get double bond. This will push, pi bond will push up. So we will get this as OH, double bond, and carbon dioxide. So this gets tautomerized to form ketone. Correct. The next reaction for decarboxylation is coal-based electrolysis. See, if you have an acid, react with KOH, I mean base, you will get a salt. When you electrolyze the salt in aqueous solution, you will get a coupled product, which is again an alkane. This we learned in alkane reactions for the formation. So what happens at the anode in electrolysis is we have this carboxylate C double bond O minus. Take 2 moles of it. It will convert into 2 moles of R C double bond O and O dot, a radical form with 2 electrons released. And this radical form, which is released here, will be unstable. So this is the rate determining step here. So which will convert into 2 moles of R dot and 2 moles of carbon dioxide. And it is this 2 moles of R dot which will terminate with each other to convert into R and R. That's how it gets coupling done. Okay, or simply I'll write it as R dot plus R dot. So that will give you R and R. While what happens on the cathode here? Cathode side we have only water. So water will take the electrons which were released from anode, get reduced to H2 and increase OH minus concentration. So if I put the overall reaction, 2 moles of R COOH, CO minus R CO minus plus 2 moles of H2O. Together it is giving R and alkane plus 2 moles of carbon dioxide plus H2 plus 2 moles of OH minus. So it's clearly noticeable that there is an increase in the OH minus concentration. So as reaction proceeds, pH of the solution increases. pH of the solution increases. Okay. So this is what we expect out of coal-based electrolysis. Few important noticeable things what we need to learn from here is, by chance, check these examples. If you have HCOO minus, right? So at anode, you will see this will become HCOO minus, releasing this as H dot and CO minus. So multiply this with 2 times, sorry, H. Uh, First you'll get this as HCOO dot plus electron. Multiply this with 2 times. And then we have HCO dot directly giving us H2 gas plus CO2. No radical form, directly it will terminate to form H2 and CO2. So basically, we are getting H2 gas on anode also, and cathode anyways will consume those 2 electrons like this, 2 H2O plus 2 electrons, and that will give you H2 plus 2 OH minus. So important point to be noted here is H2 gas is released from anode also as well as cathode also. This is the first important part in the example. Second example. In case if you already have a double bond here with CO minus and CO minus, this on coal-based electrolysis will give us dot and dot here. Okay, sorry. COO dot and CO dot here. And after releasing these 2 moles of carbon dioxide, you will get dot and dot here. That will convert into a triple bond. So you'll get an acetylene gas. Up to 4 carbons, you will only take it as gases. C1 to C4, whether it's a double bond, triple bond, single bond, everything you should consider it like gases. Second, next example. In case of uh, butanoic acids, that is, I have COO dot CO minus 2 moles will convert into COO dot plus an electron, plus 2 electrons, and this CO dot will convert into this dot plus CO2. Now notice here, because we have these 2 moles, there are multiple things that can happen. First, this dot and dot can terminate to give product as like this. So that is N-hexane. Next, this dot can in fact take the hydrogen dot here, convert into propane and propene. So this is disproportionation. Disproportionation step. Okay. Next, this dot can actually react with some more dot which was already established here to get into COO and this one. Okay. So this is ester. So we need to report this as well. So if the question is asked like find the number of products, then this is product 1. 5 find the number of hydrocarbons. If the question is about number of hydrocarbons, answer is 3. 1, 2, 3. If the question is about number of organic products, the answer is 1, 2, 3, 4. So you need to consider ester also. So don't get confused here. So these are the products that you need to mention. And lastly, in case if you have, a highly bulky group like this, dirty butoxide, and that is being subject to coal-based electrolysis. So you will get this as dot, uh, yeah, dot plus 2 moles of carbon dioxide here. So what you will notice here is, sorry, first I'll get uh, COO dot plus 2 electrons, okay, for 2 moles. So here we will notice some part of this CO dot, because that is the rate determining step, will convert into this dot plus CO2. But here, when it comes to major product, because terminating the dot and dot is very difficult, so you'll get this dot plus COO dot and make this into an ester form. So this is major. So you will not report alkane as major. This is major. Of course, the other compounds will form, but this is major. Okay. So all these have been very standard questions in JEE. So learn this. In the first case, this has been asked many times, that what are all the gases you will get. Second case, what is the gas that is being formed. Third case, how many number of products. Fourth case, major product. Okay. These are all important areas from coal-based electrolysis. The next one is a new reaction, which is Hoffman bromamide degradation. You can remember it like HBD reaction. The overall reaction is you take any amide, react with 4 moles of NaOH in the presence of bromine or uh, uh, chlorine, iodine. But since it is mainly done by bromination, so we call it as Hoffman bromamide degradation. Then we have RNH2 formation and Na2CO3 and NABR formation. Correct? So if you may have seen it, this reaction here, I mean the mechanism wise, first thing, RC double bond O NH2, and amides are generally neutral. So since they are neutral, OH minus can actually extract, I mean it can take H plus, keep it in equilibrium to get RC double bond O NH minus and H2. And this RC double bond O NH minus, as you treat with Br2, okay, so this minus will attack on bromine. This bromine will be relieved. That will go to give C double bond O NHBr plus Br minus. So it is like N bromo amide N-bromoamide has formed. N-bromoamide, when you treat this with OH minus again, this time removing H plus is even more easier because bromine is a withdrawing group, so that will help in increasing the acidic strength. So you'll get N minus and Br. We came across this kind of situation before, which we call it as Wolff rearrangement. That is, we can notice that there is a good leaving group which is present here. So bromine is a good leaving group. Nitrogen can push the electrons onto carbon, and that will make this R to connect on nitrogen. So this is a rearrangement which we observe known as the Wolff rearrangement. And due to the Wolff rearrangement, what do we get? R, N, double bond, C, double bond, O. Okay. This intermediate is named as isocyanate. So we get this as isocyanate plus Br minus. Okay. Isocyanates would make a strong reactions here. So what is the reaction that will make? Let's see. So we'll have this as R, N, double bond C, double bond O. This, because this is in an aqueous solution, we can expect this OH minus, and a basic solution, we can expect this OH minus to connect onto oxygen, get this as minus. Because of which we will get this as Rn minus COH and double bond O. So OH and double bond O. Now this can take H plus from water, being in aqueous solution here. So this can take H plus from here. So you will get this as RNH, C, double bond O and OH. And this could happen multiple times. That is, if OH minus, okay, sorry, see the other way to show it out. You can show it this way, or the mechanism can be shown this way also, that from this case, there is an intramolecular proton transfer happened here. That is R, N, H with C, O minus and double bond O. And this would make a very stable molecule which is carbon dioxide. So nitrogen would get this as NH minus. So we'll get this as R, NH minus and CO2. And now I can show the hydrolysis part. So as you make the hydrolysis now, NH minus can take H plus and convert that into RNH2. So this is a product that you will report, that is an amine and carbon dioxide. Okay. So two important reactions that are happening here. First, formation of isocyanate. Up to this is a formation of isocyanate. And from there, hydrolysis of isocyanate. How the hydrolysis happen for isocyanate. Clear? So this is how we can get the amines. So what have you noticed? See, the simple technique here is from the amides, just remove this C double bond O and connect these two. That's the final product. Okay. How many times we have used the OH minus? Let's focus on that part. So we have used once here. This is one OH minus. Then I have used OH minus once here. The third time I have used is here. This is the third time which I have used, correct? And last time, basically, this carbon dioxide which is formed here, that will be again used with CO2. Sorry, this CO2, correct? I can use this as OH minus one more time to get this as HCO3 minus, and that can be used by, because have you noticed this one? This OH minus is already released from water here. That same OH minus can be again taken. OH minus can be again taken to take one more H plus to finally convert into H2O and CO3 2 minus. So in total, we have taken these four OH groups here. Check properly. This OH is not the one which you have used, that was generated through water. Okay. So ideally, we took 4 moles of it. That's why in the reaction, when you write, you can see there are 4 moles of NaOH used. Okay. This is an important area from this topic. What is HBD reaction? Hoffman bromide degradation. Why the word degradation? It is a step down reaction. Step down, that means it is getting degraded by one carbon. Degraded by one carbon number. Okay, so one carbon number is decreased. Clear? Next. Br comes as an electrophile and leaves as a nucleophile. So you can notice that where we have Br, when it is entering here, it was entering like an electrophile. While when it is leaving here, it is leaving like a nucleophile. And lastly, the intermediate which is formed is called as isocyanate. Okay, there is an isocyanate formation. So I'll give you 2 minutes of time. So please check this reaction carefully. This is the important area. Let's check further. What are the limitations of HBD reaction? First, we cannot have number of carbons crossing 6. 1, 2, 3, 4, 5, 6. So if they are more than 6, then making the migration becomes very difficult. This migration becomes very challenging. Okay, so that is one important limitation. So this is valid only up to carbon 6 or less than 6. Second, in case if you have alpha haloamines, they don't give amines as the final product, but they will give corresponding aldehydes or ketones here. Let me show you what does that mean. Suppose if you have an alpha amide, C double bond O, NH2, and some halogen. It could be chlorine, bromine, or iodine. And this, when you react with Br2 and NaOH, we know that first we will get OH minus replaced here because halogens will get replaced by OH by SN2 substitution. And then furthermore, as you react with Br2 NaOH, but I'll do not write Br2 here because we have to use anyway basic medium. So with this Br2 NaOH, now we'll get double bond O and N minus and Br. I'm directly writing this Wolff rearrangement step. Once you get here, so from here I can say that this part will be moving on to nitrogen. It will close to double bond, remove Br. So this is the Wolff rearrangement. So we will get this as OH connected to N, double bond C, double bond O, isocyanate. And another one is Br minus. Notice this isocyanate, when you hydrolyze it on hydrolysis with OH minus, we learned that it is supposed to get this as NH2 and OH. Now, because it is in basic medium, what would happen here? This OH minus will take away H plus from here and this will have NH2 and O minus. This O minus will push the electrons and try to remove this NH2. That's the problem of OH minus having at alpha position. So that will end up getting an aldehyde instead of amine. So this NH2 minus will go away and what you will get here is an aldehyde. So you got the limitation here. So we should not have any alpha hydroxy or any alpha haloamides. Third one, in case if you have a C triple bond C at the alpha position itself. Okay. For example, I have CH3 CH2. Okay, then we have C triple bond C with C double bond O NH2. This amide, when you treat with Br2 in the presence of NaOH, I'll directly write the isocyanate form here, so which is CH3, CH2, C triple bond C with N double bond C double bond O. This is isocyanate. And isocyanate on hydrolysis, we expect this to get this as amine. So CH3, CH2, C triple bond C and NH2. This is the amine which is formed. Now, what would happen here is the amine in basic medium, because C triple bond is a very strong withdrawing group. So that can take this H plus and make this into CH3, CH2, C triple bond C with NH minus. That minus will keep on pushing electrons till that C minus from H2O will take up CH3, CH2, CH double bond C double bond NH, and do it two more times here. So this again reacting with OH minus, take the H plus away here, it will convert into CH3, CH2, C, CH double bond C double bond NH minus, sorry, N minus. And that will be pushed again towards carbon, and carbon taking away H plus will convert into CH3, CH2, CH2, CH2 and C triple bond N. So what are we exactly getting here? Cyanide. So this is the final product that we will report. So we will get, instead of amine, we are getting cyanide. Final product. So I suppose you found out the important limitations in this case. Okay. While, what are the other notes which we need to check here? Notice that in some books it is being said if you have C double bond O and N and Br here and minus, we will notice, but this is not correctly quoted in all the books, but they have seen that uh, it could so happen that Br minus could go and we will be left out with one lone pair here, correct? And one more lone pair is already there with it. And now an empty orbital with Br minus. This is called nitrene. Okay. But in many reaction mechanisms suggest, all strong references suggest that there is no considerable amount of nitrene form. So therefore, we say nitrene character is observed, but not complete nitrene form. It is observed during Wolff rearrangement, but is not exactly nitrene separated out. Okay. So this is all the important area what you need to learn from uh, HBD reaction. Okay. And now let's go through some important problems which are very standard questions which we must know, right? So starting from problem 1, please check. If you have an anhydride like PHCOO twice O, this is an anhydride, and that if you hydrolyze it, let's say I get a compound A, That compound A, when you react with NaOH, will get compound B. And that B, I react with NaOH and CaO and heat, I'll get compound C. And that C, if you react with Cl2 in the presence of AlCl3, I'll get D. And this D, if we react with magnesium and ether, we will get E. And this E, if you react with carbon dioxide followed by hydrolysis, we will get F. So we need to find out A to, sorry, again we are getting A. That's what meant, okay? A to A. So we have to get A to A. What are all the products here? Look, first A. After hydrolysis, I'm sure you must know that we are getting benzoic acid. B is benzoate ion, CO minus. C is soda lime decarboxylation, so I'll get benzene. D is halogenation, ES, that makes it D. E is Grignard's reagent, so I'll get this as minus and MgCl plus. This is Grignard's reagent. And F is again getting back to benzoic acid. Very important conversion. Simple one, but uh, if you could revise all the reactions, these kind of reactions are important. Next, check out problem 2. Imagine I have cyanide and methyl here, and we are using this. We are hydrolyzing it to get compound A plus B. B on reaction with NaOH will get gas C, which is pungent. Next, A, when you react with MnO4 minus with basic medium and heat, I am getting this as D. This D, when I am hydrolyzing, I'll get this as E, and E, as you react with KOH, I'm getting this as F. F on reaction with NaOH and CaO and heat, you'll get this as G. G on reacting with CH3Cl and AlCl3, we'll get this as H. And H, again if I react with KMnO4 and OH minus, I'll get this as I. And I, with coal-base electrolysis, Ke means coal-base electrolysis, will get J. So I need to find out A to J. Let me take you through one reaction here. First, you're making an hydrolysis, so that makes it COOH and methyl here, so which is A. B will be ammonium ion. C will be ammonia gas. D will be, because you are making an acid form, I mean oxidation, side chain oxidation, so you'll get D. E will be after hydrolysis, again you'll get terphthalic acid. This is terphthalic acid. F is again the same thing, we'll get this as CO minus and CO minus. This is F. F and D are same. And then G is soda lime decarboxylation. So this is G, because CO2 will go away and you'll get benzene. H is, we are making Friedel-Crafts alkylation, so toluene. Then again oxidation will give you COOH, which is I. And Colway's electrolysis will couple the two alkyl groups or aryl groups. So you'll get this as J. So this is J. So please check. Clear? Right. Check problem number 3. If we have if we have toluene given CH3, that I treat with carbon dioxide followed by hydrolysis. Okay. We will get this as A and C. Then I'm treating with first KMnO4 in acidic medium and heat. Second, I'm treating with SOCl2. Third, I'm treating with CH2N2 with Ag2O and heat. Fourth, I'm performing hydrolysis to get B. Okay, I'm getting this as B. Clear? And B, I'm treating with NaOH, CaO and heat. I'm getting this as C. Got it. C, I'm uh, treating with Cl2 excess and H nu to get this as D. And this D on hydrolysis, right? H plus and hydrolysis, sorry, D, forgot one thing. Yeah, not excess, my mistake. 4 moles. 4 moles. Okay. 4 moles. We are getting this as uh, D, 4 moles. Then we are doing hydrolysis in basic medium to get this as E. E, when you further react with OH minus concentrated, we are getting this as F. F on hydrolysis, we are getting this as G. Okay. And this, when you react with soda lime decarboxylation, again I'm getting this as H. And this H, when you oxidize this with PCC, I'm getting this as I. This, when you react with AC2O in the presence of ACO minus and heat, I'm getting this as J. And J, as you treat with H3O plus, you will get the K. And K, when you treat with Br2 and CCl4, I'll get this as L. And L in the presence of NaOH, sorry, K2Cr2O7 and heat. K2Cr2O3 and heat. I'll get this as M. Okay. This M, when you react with NaNH2 and excess, you'll get this as N. And N, when you react with CH3Cl, L, sorry, MnO, and CH3Cl is O. O, when you react with lithium in liquid ammonia, lithium in liquid ammonia, we'll get this as P. Got it? So now let's try to find out A to P here. What are all these reagents that are being used? So let me start with A. So first you're making a EAS reaction. Carbon dioxide is a good electrophile. So that electrophile will go here and convert into COOH. Next B. B, we will make this also into acid. So we'll get this as COOH and COOH. And here I need to mention two equivalents, okay? Two equivalents. So then C will become, here this is not C, this is a continuation process, not B here, sorry. We have not got to the B yet. This is an ongoing process. So first with KMNO4 you will get this. Then with SOCl2 we'll get this as COCl and COCl. That is, we have Ansted-Ide reaction, which makes it COOH, ketene form. Ketene form, when you hydrolyze it, you will get this. So this is B, everybody. Okay, Ernst-Eisted reaction. I told you that today. So from ketene, you will get this B. Now from B, we can get decarboxylation done. So we'll get CH3 and CH3. This is C. Then D is, you are using only 4 moles of chlorination done. So you'll get CHCl2 up, CHCl2 down. This is D. Then E is hydrolysis for the same. So hydrolysis will make it CHO and CHO. And next F. F is about using OH minus concentrated. So you can see there is an aldehyde and aldehyde within the molecule. So that will be making a Cannizzarose reaction. So one will convert into an alcohol, the other one will convert into an acid form. So this is F. And after hydrolysis, that will convert into COOH. This is G. Then we are performing soda lime decarboxylation. So this CH2OH will remain, and here you will get this as H. So benzyl alcohol you will get. I is using PCC, you will get oxidize this to benzaldehyde. Benzaldehyde, when you react with AC2O and ACO minus, this is Perkins reaction. Perkins reaction will make it pH CH double bond COO minus. And K, that is after hydrolysis, we shall get this as CH double bond CH COOH. L is bromination on double bond. So we'll get this as CHBr, CHBr and COOH. Okay. And next, now when you have K2CO3, this will become CO minus. And on heating, see on there is a benzene form present here. So this is alpha and beta. At the beta position, if you have benzene form here, decarboxylation will take place. So after L, we'll get M. M is a decarboxylated product. So we will get this as CH Br and CH2Br. This is what you'll have, okay, on heating. K2CO3 is not required. I can directly write this as heating, just heating. And then M is done. N is about, you know, elimination. On elimination, we'll get this as C triple bond C minus Na plus because I'm using excess. And N minus, I mean this C minus will attack on CH3 to O. We will get this as C triple bond C and CH3. This is the product form. And what will be P? P is a Birch reduction. Birch reduction will make it and trans addition. So we'll get hydrogen here and hydrogen here. So this is the product that you will get. So please go through it once quickly. Check A to P properly.